Hi everyone, this is the second video for section 5.2 that's on primes and composites. So now we're going to transition to kind of talking about just some of the important facts to know from this chapter. So the first one is the fundamental theorem of arithmetic. So this theorem is fundamental, like it says, and one thing that you find if you study math more is that pretty much every discipline of math has what they call a fundamental theorem of this. There's a fundamental theorem of calculus, there's a fundamental theorem of algebra, a fundamental theorem of arithmetic, and yeah, pretty much every discipline has what they call their fundamental theorem, meaning that it's one of, if not the most important thing that you need to do anything in that field. Okay, so this says that every natural number greater than 1 has a unique prime factorization. So, for example, right, if we take any number like 6, we can write 6 as a product of primes, and this way to write this is unique, right? You cannot write 6 as a product of any other primes besides 2 and 3. And this holds, right, for every composite number, you just find the prime factorization in the ways that we talked about in the last video. But one thing to note, that if your number is prime, so right, 3 is its own. 3 is its own prime factorization. So this is just 3, which is kind of odd to just write it as 3, but every prime number is its own. I'll write this down. Every prime number is its own factorization. So the prime factorization of 3 is just 3. Let me move this a bit to the side. So 3 just is 3. Okay. Okay, so that's one thing that's really nice to have. So this is really important just because it makes things easier. Think about it. If you have any number, rather than working with that number, we can instead look at its prime factorization and work only with prime numbers. And that's kind of how this field of number theory got started, is that, well, working with really big numbers can be kind of hard, but we can change all of the numbers that we're looking at to just be looking at their prime factorizations, and then we're only dealing with these prime numbers. So that's why people who do number theory really just study the prime numbers and their properties, and there's a lot to do with prime numbers. So that's why we care about them, is because we can take any large number and instead think about its prime factorization. Okay, one other interesting thing is called Goldbach's conjecture. So Goldbach's conjecture is not proved or disproved. It's a conjecture. So what a conjecture means is that this guy named Goldbach said, I think this is true. And pretty much everybody agrees at this point that every integer greater than 2 can be written as the sum of 2 primes. So most people agree with this, but no one's proven it, no one's disproven it. And so your textbook has a really nice kind of discussion on this on page 175 of the book. So I would go through and read the discussion that's on in the book, just because it talks about it in a really nice way, and it has a really nice picture to go along with it. So definitely go through and read the discussion on page 175 on Goldbach's conjecture. Okay, so those are just kind of two important, right? This section's called important theorems. So those are two important theorems to know. So just like the definitions from this chapter, make sure you know what these say. if I say on an exam, what's the fundamental theorem of arithmetic, or state it, you should be able to state this exact sentence, and the same for Goldbach's conjecture. Okay, so the next definition is square root. So the square root of a number n is a number whose square is n. So we can kind of write this in math symbols. So the square root of n is some number x, where x squared gives us n. So square root of n is a number x such that when we square x, we get n. So we've seen definitions like this before, where we define a number in terms of it having this property once we operate on it. But that's what it is. And so you can see that this equation kind of follows from the square root of n equals x, because if you square both sides, you get n equals x squared. And that's exactly what we want to happen. Okay, so this is square root. And the reason we are bringing this up here is because of this test for prime numbers. So if we want to check if a number is prime or composite, we realistically, it just kind of going into this naive, we would need to check, okay, so for example, this number 101, we want to check if it's prime or composite. So we want to see if every number smaller than 101, does it divide it or not? Does 101 have any factors other than 1 in itself? Meaning we would need to check the numbers 2 through 100 to see if they're a factor of 101, which checking all of those numbers is a lot, and we don't want to do that every time. So there's this nice little trick that's the test for prime numbers. So the test for prime number says, to test for the prime numbers, you only need to check for prime factors that are less than or equal to the square root. So you only need to check for prime factors that are less than or equal to the square root of n. Okay, so let's kind of see how this works. So we don't know what the square root of 101 is, but we can see what is around 101. So 101 is really close to 100. So we can see that 100 is less than 101, which is less than 121, right? So from this, that means that we can kind of take the square root of everything. So the square root 100 is less than the square root 101 is less than the square root 121, and I chose these numbers strategically because the square root of 100 is 10, and the square root of 121 is not 121, it's 11. Okay, so kind of seeing where 101 falls on a number line between 100 and 121, we can see that the square root of 101 will be somewhere between 10 and 11. So we just need to check all numbers, all primes that are less than 11. So we need to check all prime numbers less than 11. Okay, so we just kind of think about it. This is really nice that we're only having to do up to 11 because we can use all of our tests for divisibility, which is really nice. Okay, so I'm going to write out kind of all the things we need to check. So 2 divides 101, 3 divides 101, 4 divides 101. And you'll notice you want to make your divide symbol here kind of taller than the numbers that we're looking at. Oh, we actually don't need to check all of these. Just need to check the prime ones. 5, 7, and then the next one is actually 11. Yeah, so you want to make sure that your divide symbol is taller than your numbers, especially right here in this last one, 11 divides 101. If we made the divide symbol the same height as our ones, this would look very confusing and be hard to read, so just make sure that it's clear that you have an 11, and then the divide symbol, and then 101. Just make sure that's perfectly clear. Okay, so now we can use our test for divisibility and check these things. So 2 does not divide 101, since 101 is odd. Okay, that's just using our normal test, right? Even numbers are divisible by 2. Now what about 3? Remember that our test for divisibility by 3 is adding up the factors. So the sum, adding up the digits, I'm sorry. So the sum of the digits here is 1 plus 0 plus 1 is 2. So 3 does not divide 101, since 1 plus 0 plus 1 equals 2 is not divisible by 3. Okay, so now we're going to check 5. So 5, again, does not divide 101, since 101 does not end in a 0 or a 5. Okay, 7. So remember our test for 7, we didn't have one because we can have one, but a lot of times it's just easier to just divide by 7. So we then do 101 divided by 7. 7 goes into 10 one time with 3 left over. 7 goes into 31 4 times with 4 left over. So 101 divided by 7 is 14 with a remainder of 4. So 7 does not divide 101 because we have a remainder. Similarly with 11, we didn't write down a test because a lot of times it's just easier to do this, to just divide by 11. So this goes in 9 times. And then we have 9 with 2 left over. So 101 divided by 11 equals 9. Remainder 2. So again, because there's a remainder, 11 does not divide 101. So based on our test for prime factors, we've only needed to test the primes up to 11. So by this test, 101 is indeed prime because there's no other things to test. Okay, so this is an example. The first example that we're going to do of using this test for prime factors to determine if a number is prime or composite, and we will do more in the next videos.